let me tell you more about the problems that we normally encounter when building and deploying machine learning pipelines, and how we ensure we minimize them by implementing the correct design of the machine learning pipeline right from the start. Reproducibility is a real problem that exists both in businesses and in academia, and the consequences of the lack of reproducibility can have significant financial costs, not to mention the loss of time and the potential loss of reputation. So it is important to try and get this right from the beginning. So what do we mean by reproducibility in machine learning? We define reproducibility as the ability to duplicate a model exactly such that given the same raw data as input, both models return the same output. Remember that we do not just deploy the machine learning algorithms, we rather deploy the entire machine learning pipeline. So we need to make sure that every single step of the pipeline is reproducible. So let's recap on the different machine learning pipeline steps. We first inject the data to our pipeline. Then we transform the variables in the raw data so that we can now use them to build the machine learning models or to get the predictions out of pre-built models. Then we select the features, and then we finally get the data to the model so that we can either train the model first or make the predictions once the model is trained. So what do we need to do to ensure reproducibility? And more importantly, at which step of the pipeline do we need to ensure reproducibility? Well, pretty much at every step of the pipeline. So we need to make sure that all the steps in red are reproducible. This means that all these steps should produce identical results given the same data, both in our research environment and in our production and deployed models. I will describe a variety of problems that we have encountered when building and deploying machine learning pipelines, and then I will show you frameworks that you can put in place to try and minimize these problems. First, let's discuss about the way we inject and consume the data. This stage represents the most difficult challenge to ensure reproducibility. The problems here occur if the training set utilized to train the pipeline can't be reproduced at a later stage. For example, if we can't reproduce the training set in the production environment. And why would we not be able to reproduce the original data? First, some databases are constantly updated. And if we didn't think of reproducibility ahead of designing the database, what happens is that when the database is updated, it often overrides previous records. So the value that was present on a certain date may be overwritten by a new value entered in a week's time. This means that the data that you use today will not be the same as the data that you use in a week from now. Another problem is the order in which the data is loaded when using SQL. SQL loads the data randomly, so if the way it was loaded in one environment does not coincide with the order in which it was loaded in the other environment, you may find reproducibility problems. And this comes from the fact that when we separate data into train and test set, we utilize a random function. So what can we do to minimize the impact and ensure reproducibility when we inject our data? One way is to save a snapshot of the data that you're using to train the model. So load it from your database and save it somewhere else for future use. This is good and useful if the data is loaded from many different sources actually, and it is particularly useful if the data is not very big. But it has a few downsides. First, with the new regulations on the use of data, you may not be allowed to store data somewhere else other than in the source. And second, if the data is too big, you may not even be able to store it somewhere else. So alternatively, it is recommended to design the data sources with accurate timestamps so that you're able to obtain a view of the data at any one time point. This represents the ideal situation. However, if you were not lucky and your databases were not designed like this in your business, it may require a big effort to redesign all your data sources. Finally, to try and account for the fact that SQL loads the rows randomly, when loading the data, try and use some other variable to ensure that the order in which the files will be loaded are the same in the production and in the research environments. Next, we need to ensure reproducibility during feature creation or feature engineering. Lack of reproducibility may arise from different points. For example, when replacing missing data with random extracted values, or when removing labels based on percentages of observations. It may also arise from calculating statistical values like the mean to use for missing value replacement. And it may arise as well from more complex equations to extract features, like for example if we are aggregating over time. The good thing is that by applying a few coding best practices, we can minimize the lack of reproducibility across environment. First, code on how a feature is created should be tracked under version controlled and published with auto-incremented or timestamp hash versions. Many of the parameters extracted from feature engineer depend on the data used for training, so we need to ensure that the data is reproducible, as we discussed in the previous slide. If replacing by extracting random samples, remember to always set a seed. In fact, avoiding replacement by random extraction of values altogether goes a long way to ensure reproducibility. The training of the machine learning model per se also poses challenges to reproducibility. And this is because many machine learning algorithms rely on an element of randomness for training. For example, algorithms based on decision trees extract subsets of the data at random and also extract subsets of the features at random. If we're working with neuronal networks instead, the way we initialize the weights is also at random. On a different level, some machine learning libraries work with arrays instead of data frames, and these arrays are agnostic to the features. So we need to be careful with the way that we feed the features into the model, because if we change the order of the features, we will be obtaining unreliable predictions. In order to mitigate these challenges, we need to record or store the order of the features that we use to train the models. We also need to store the feature transformations that we apply before training the machine learning models. If we optimize the hyperparameters of the models, we need to store the values of the hyperparameters. If the models require randomness for training, we need to set a seed for reproducibility. And if our final model is an ensemble of various models, and I will say a few more words about it in section 4, then we need to store somehow the structure of this ensemble. There are also challenges to reproducibility during the integration of the model in the production environment. Very often, a feature that we used to train the model is not available in the live environment. Therefore, we cannot really use that feature to obtain our predictions. Often as well, there are different programming languages in the research and in the production environment. There are different softwares, and sometimes the populations that we obtain through the live production environment do not match the population used to train the machine learning models. To ensure reproducibility during the integration of the model in the production environment, software versions need to match exactly those used in the research environment, and the applications or the model API should list all the third-party library dependencies and their versions. Ideally, we would use a container to track the software specifications. As much as possible, we would research, develop, and deploy the machine learning model in the same language so that we can port the libraries that we used in the research environment to the production environment. And this is key that before building the machine learning model, we understand how the model will be integrated with other systems. So these erroneous integrations normally come from the fact that data scientists do not fully understand how the business systems will consume the model when they set to build the model. And also, it comes from software developers not fully understanding all the intricacies of how machine learning pipelines need to be integrated. So with practice and a few cycles of iteration of model deployment, both groups learn to work together, and these problems begins to be minimized.